So here just is using this to define or just using the definition to show this subset. In fact, we know that the subset, the definition, just using logical symbol condition. So we can show just already to give you about this here. Here just say is equal. So the equal we just have used by condition here. And the subset we just using the condition here. We say this A is the subset of B only if and only if for all x, if x belongs to A, then x belongs to B. So just from this definition, if we want to show A is a subset of B, then we can show for all x, this is a logical expression to show whether or not for all x, if x belongs to A, then x is B. So from this, similarly, here is altogether the left is a subset of the right. So we want to show for all x, if x belongs to the left, then x also belongs to the right. If it is okay, then we can say left is a subset of right. The overbar. So if using the next set operation definition, it means the intersection. Intersection is just using the logical and. It means it's just using and yeah, logical and. So if the two sets the intersection, it's just using the logical and conjunction to define this. So from this definition, if we want to show A intersection B, we can just translate to the logical expression. Here just the definition of the intersection. What's the reason from this to this? Is just the logical mechanism. We have already to understand from the rational logic or just the critical logic to the logical what we know. Sometimes we just make it the simple way, the simple rule that if you want to push this logical lot and you want to change everything to the three part. This subset, the third part. So for each part, we want to change. The first part we change a lot, and second logic operator also to change from and was and to or, and then third part in or not. So he also just using the third definition, the set definition unit, right? The section, and here just using the subset. So from this shoe or this part of the shoe, we have used three stabilization of four stabilization. We have the complement. The first is the subset, and the second is the complement, the third is intersection, and the fourth is the unit. So you will find this set operation and calculation is also very important. And we just show you about this symbol. That means this set the calculation is just using the logic symbol or intersection and subset just the condition. And the way in fact also you have this equal and we just do five conditions and with the complement we just do node. So you will find this symbol smoking node is the example. It's very just a good example because from this example we just give you the five basic or complement logic operator refer to the set, the five set operator. Means set equal or identity, set subset, set intersection, set union, and set content. Refer to the five basic logical operators. So it is similar way with the definition of the subset definition. Because from the subsection we just have a condition. Condition that means if x equal to left and x equal to right. Unit definition. It is a modular other side. So just from this process of the proof, we will find it just also using just the set, the definition in, in, in X is a subset of the right. Okay. Now we just from this subset definition, subset definition is one to shoot is one to shoot the subset of the right. That means if and only if for all if x belong to the left. Addition means if this, then so if this that means just an assumption. So this assumption just from this definition of the subset, or the subset just want to show if x belongs to the left, then x belongs to right. So just we have a very wish to x belongs to left, and then just many of the process we just x belongs to right. So the definition of the subset equal. So both the left is subset B and C right subset of left negative. So previous the proof just using the definition or it is just the first answer, first way, and the second way we can just using the set the build location of that listing the items machine. This is the calculation. You also can say the negation. In logical rule. smoking no. And also from the set population. So from this way to you will find we didn't to translate this. That means we didn't to from the definition of the set to the identity of equal. We didn't to divide this equal into the two parts just from the subset from without you just from the previous message. Do not into the tutor expression. Now we just from the set we do the logic, that means just from this the set to the set to the population, that means from the complement of it also can be seen as set with builder location or description to the set description. This description just using the logic describe the set. So based on this, the logic expression, we just bring the logic expression to work. So, so find the second way have just two the set building location because in the set building location is the proposition just describe using the propositional logic to describe the set feature. So this the set feature is actually the logic logic changes with the former and the logical underneath this state notation. That is the second way. And the third way, So in the third way, we also want to show or to prove is the marginal for the set operation. And why we just call it membership but we cannot choose it because the set you cannot say the S value that you just only say membership because whether or not X, for example, they have that for all X, we know that this definition is for all X belongs to A. So that means when that for all X belongs to A, also X belongs to B, whether or not they belong to A in the section B. The element belongs to A, and that will mean that X not belong to B. Then we want to check if X belongs to A and X not belong to B, we want to check whether or not X belongs to A intersection B. So it is just the membership table, not truth table. It is different from the propositional logic. Because propositional logic, it is and for each of the proposition logic or set operation into the it's using this membership is belong to the truth table of the logic expression. It just translate this A intersection B, that means X belong to A and X belong to B. So it is can be said it is the truth table. If we just translate the membership into the truth table from the X belong to A. Okay, this just to show you about the proof and just to give you the example. And this example just using the Morgan law. We want to show the Morgan law, and we just show you from this video, I just show the three ways. These the three ways. The first, just to translate the A equal to B, just translate into the subset, and then the second way, just use the state builder notation and using the logical equivalence. And third way just means when we translate the logical expression and the logical truth table, so it is belong to or refer to the membership table. Membership table, just show you about that. And already show you the video. This is the second. This is the second way, just using the state build notation, and then just use the logical rules for this example. Okay, we are not discussing detail, just to show you about this way. And here is similarly, just using this using the build notation. Okay, and here is the membership to prove this. Okay, it means for the membership we can just call it. So this is the similar about the smoking law from the video, and the video just shows you the example of the smoking law. This state identity, and here just to show you another way. This is just want to show you this state identity. Maybe it is more little a bit complex than the smoking law yours, but it is a similar way. That means in the distribution is the distribution. Okay, distribute. Okay, so it is distribution about this the rules, and we also show you about the three ways. The first is just the two ways from this net. We want to show you net whether or not equal to right. Then we can first to show you left whether or not it is belong or just a subset of the right. And then similarly, we also can set this right belong to or subset of the left. So altogether, from these two each other, they are subsets, then we can say they are equal or they are use the first approach. And the second, just using the set user notation. That means just from this smoking law, just the same. Okay. And there's a membership table. There's a membership table from this distribution law. And to show you distribution law, and similarly, because membership table, why we just can be similar truth table just because we have changed this. It is just like this. You will find if this we just change to X not belong to it is belong or not belong. So the membership means that if here is A, here is the set A. Why? What means this one? One means that whether or not X belongs to A. So this is a membership. This is a membership. So for the set A is not the S value, but this is we change it to membership. If we say here X belongs to A or X belongs to B, then you can find it easy to understand. 1 is yes. 0 means X not belongs to A. So here is also X belongs to C and also X belongs to B union C. And here is X whether or not belong to this, and then similarly follow it. So X belong to, so we just 1 and 0. Just the relation to the membership relation, not the value. So if you just translate this membership, then you can find it is X belongs to A. So it is just a proposition. So this proposition you can find 0 and 1. So this is a membership table. just say about the propositional logic truth table. Okay, and here just extension of Mobi law for the three value between similarly, and here just using the state builder or just using the existing Mobi law directly using the Mobi law 2 times, and then just using the commutative law. So we just using the existing law to show this. So this is the other way to show about this. It means we can use it in the existing law to show about this. Okay. And here is the general example about giving you this. That means this is the extension of Mobi, and here is the concrete example to show that they are just satisfying this extension of Mobi. Here the general case just means we can extension about this. General case, maybe we also have this general case explanation.
One more notation that you might see as you're working through the homework this week, and that is just the generalized union and intersection. And so here, and I think we've talked about it before, but I wasn't sure, so I wanted to put it in here. Remember that this would just be the union of several items, and this would mean from, the index starting at 1 and going to n of all of whatever A happens to be. And so here I would have A1, union A2, union blah, 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 all the way up to AN. Same thing at the intersection. I'm looking at the intersection of all index items from 1 to n. And so that would be the intersection or any items that all of these have in common. Because again, we're looking at the intersection. So not really a new concept, it's just a different notation. And you're dealing with quite a few different sets.
Okay, this is just the general case. The general case is union that means we can just use this equation to describe all the set union in the section. And the last slide just gives you the idea how to describe our set. Because we know that our computer or our computer world cannot understand the set directly as our human idea. Because we know that the computer only have the set or the state 0 and 1. How to use 0 and 1 to describe our set? Okay, here just to give you the coding. We can say this is the code, encode or decode. That means this code, machine code or description way. Here is all the set, okay? And here is the A, we can say is the subset from this union, and B is another subset. So just using the subset or membership. So you will find the membership table also give us way to describe the state of the state from the union. For example, here is the union. Then we can say, for example, for the S as the first element, whether or not we are just to choose this first element. If we choose it, yes, that means even the second element we are not choose, so we are just using the 0. The third, yes, and the fourth we are not choose. So for each refer to this the level. For each level, we are just determine whether or not we are choose. We are select. If we are select, yes. When we are not select, no. So that means it also can be seen for each the element one by one to check whether or not it belongs to A. This element belongs to A. We also can say this element belongs to A, so it is 1. So it can be said it is a membership table. So this can be membership table. Membership, this is A membership now. Then also you can membership table just using the logic expression to to compute the membership, okay, and then to uh, describe or to show about the set union or set operator. So set operator translate into the logical operator. Okay, this is coding, encoding of the set like this. Okay, 5 minutes break.
This video isn't right.
Okay, now we continue to talk about our set, and now we have show you about how to prove the set, and we have the 3 ways. First is just to show you about is we have 3 ways. The first is just from the definition and from the set, and the second is just using the set indication, and the third is the membership. Okay, And from this membership, we also can be show you or just give the way or understand why computer to do their set operation. That means the set operation in the computer is just translated to the logic expression or logic operation. And based on the logic operation, we just do this. So you will find it a different way from our humans understand the set operation of the computer world. It means the computer was just translated into a logical expression. And based on this logical operator, we just compute this state. So that is why our course to describe this mathematics or discrete mathematics. That means it is referred to the computer mathematics. It means they are just from the computer world or computer idea, computer side to understand or to understand why the computer can work for us. Okay. Now we will move to the next the topic is the function. And we have already to understand what the computer to describe the set. Also, in fact, we just have the Cartesian set. We have no remember that in the Cartesian set, and B time A time B, the two set in Cartesian set, it just means it is just the figure. That means it is A, B, and here A from S set and B from B set. Okay. So it is a Cartesian set. We also know that if any just R is a subset, is the become set, it is a relation. Becomes a relation. And this can be seen the relation A and B, they have relation. If we have their relation, we can just use some this. I just use the relationship connect with. And now the function, what means function? In fact, the function can be seen as a special relationship. So here is the definition, and here definition is from our human side. That means a function from set A to B denotes this. I should be careful. This arrow is not the logical addition logical. Or with the logical symbol because it is just the human idea or human side. So it is from A to B the function, and this just shows that exactly one element of B to each the element A. That means even for each the element A, for example, this each element, we just find should be careful exactly one element. That means what means existing one element? That means we then to from, for example, here is the element. We cannot say you can find the two here and here from B to map or to match this. It isn't to satisfy this condition. Exactly one element in B refer to each the element of A. So that means we can say it is only find only one. So you can imagine before this function for in the computer just to say if we just input or writing some code and give you the re-input and then this program give you output. And you can imagine if you just input one value, but the output give you the different value from the different time because now you run uh, your code from this way, the same input. From this time, he give you one. From next time, he give you three. Then you will find it is unstable. It is unstable. It is output is cannot determine from the input. So if output is only determined from input, then we can say it is a function. So function is a special relationship, but it have some special condition. And this special condition just means that for each the output should be exactly or only determined from the input. And for each of the input, we only give you exactly one output. So it is a special or you should remember this. Otherwise, it's maybe exception or maybe some wrong about your programming code. Okay, now we just to understand well about many of these definitions from the video. Maybe this come clearly. Okay.
Introduction to functions, and any introduction video for my courses, a lot of this is just terminology, so that as we continue to study functions, when I use words like range or pseudo-domain or domain, that you understand what I'm talking about. So let's take a look at what we know about functions. A function f from set A to B, and notice how we denote that function, assigns each element of A to exactly one element of B.
So exactly when.
A is every element of A must be mapped to some element of B.
So we can permit the two input, for example, 1 and 3, to refer to one output. Means, for example, you just have the function fx equal to x squared. Then you will find if you just input the positive 3 and negative 3, then the output is the same 9, no problem. Okay, that means we can allow the many inputs refer to the same output, but we don't permit the same input and give you different output. We don't permit this because we have this condition exactly one element of B should be careful to remember to understand this.
Be considered a function. You might also hear of a function being called a mapping or transformation, which is going to be describing functions. And obviously, it's important for us to know some of the terminology that we might see. So if we're talking about the image, let's say we know that f of 1 equals b. And I know that because that is this line right here. 1 maps to b. So if the input is 1, the output is b. So then I can say that b is the image of 1 under f, which would of course be that 1 is the pre-image.
The image can be seen output, the image can be seen input.
Under f. But be careful because notice 3 also maps to b. So I have to say 1 and 3, or the set of 1 and 3 more specifically.
So for each the element, the image should be only one. But for the pre-image can be have the many, many the pre-images for the same value.
We could also say, if we're dealing with the entire function instead of just one value or element of the set, I could say that the set of A, B, C is the image of F.
Why we didn't include DE in the set of these elements? Because we have no just input to give you the output. So imagine all the image can be seen all the possible output. So here DE maybe is not exactly one input to give you this output. So can be seen it is an exception, or maybe it is no, never you will get this output value. So imagine only one A, B, C. That means have the just the connect to this A, B, C, but the D and the E, these the two elements have no element connect with them. So they are not image.
Also, let's talk about the range. Again, this is the domain. A is the domain, the set of all x's. D is the codomain, the set of all possible y's. And notice it's not necessary for each element of the codomain to be mapped to from the original domain. So the range is the set of all images, so the outputs that are mapped to from the first set. So in this case, the range would be those values A, B, and C, because these are all values that were mapped to from the domain of A.
So from this example, the range is equal to images, all the images.
One is an explicit statement. An explicit statement just means that we are going to be told exactly which elements map to exactly which other elements in the codomain. And so this would be an explicit statement telling me that A maps to 1, B maps to 2, and C maps to 1.
So it is just as similar as a discrete. For each of all the possible input, we just give you the output. So we have described the step by step or one by one to give this relationship. Then we can say it is can be described the function.
So that would be an explicit statement because there's no formula or function. It's just here's what maps to this. In a formula, obviously, we're just going to have the normal formula. F of x equals x squared plus 1. We might.
So this is just a discrete, and this can be seen as a continuation function, discrete function.
I also have a computer program. More on that as we continue to study discrete mathematics. Or you might have a relation. So we talked briefly about relations, and we will go into them in much more detail later in this course. But if I have a relation, and remember, this is telling me that I've got some ordered pairs, 1, 2, 2, 3, 4, 5, 1, 7, 2, 6, etc. We could have a function if we only have one ordered pair for every element of A, which means this subset could be considered a function because I have not reused the x value of my ordered pair. Notice I did not include these two, which did reuse the 1 and 2 from before.
So if you just from this expression, then if you just using this relation or Cartesian set, because we just show you about the Cartesian in the previous sessions about this, just to give the pair between the S element and then the second instead element. For this, we can say is the A1 is A1, B2, C1. So just like this, we just combine together. So we also can use this Cartesian set to describe function. So that is an interesting thing. That means you will find in computer world, our function is can be seen as the map, as the relation, as the special set. So it is a computer program. You are just to implement or your just your this function, and you will find this the function can also can be described here. Maybe this map for a human, but here maybe it's just for computer. So the computer program maybe finally be tested to the special set. And special and set we have already shown you that set can be described as a logic expression. So that is why we can use a 0 and 1 to describe our the concrete programming or the favorite or our the complexity the human words. Just like using this way.
Here, notice I did not introduce two, which did reduce the magnitude from the field. Here are a few questions for us to try just to make sure that we understand all of the terminology involved with functions.
So here just maybe some is the concrete or just the boring the concept. But maybe just from this concrete example to help you to understand this many the concept domain code. Domain means that you can just say that all the possible the input value. Code domain just means output value. The range is all possible output. And pre-imagine that means pre-imagine just give for each element that means the input. Because you just get the output too, so you can to guess or you can to influence maybe whether or not all the possible the input.
Answer, what is the domain of a function that maps x to y? And the domain is the set x. You can see x represents A, B, C, D. The codomain would be set y, which is all of the values in that codomain. The range would be only the values of 1 and 2. So the set of values containing 1 and 2. The pre-image of 2 says what value mapped to 2, and then you can see here that that would be D. And the images of A, which would be what does A map to? So the image or images of A, and that maps to 1. And F of D means what does D map to? And D maps to 2. Now that we are familiar with functions, I'm going to look at a couple of particular types of functions known as one-to-one functions and onto functions. One-to-one functions, hidden function, range, and call.
And now we just give you some idea about some function concept. And from this concept, we can understand what it means domain, codomain. So domain, we can say is the input. It's like this is all the input. Codomain just is, and it's just the output. And the imagine just means you just here the element of the codomain can be said imagine or reimagine is just the element of the domain. And the range you can say imagine, all the imagine of it. All the elements it is just connect with from the domain. Is okay. And this function of the state here just to video. And now we just to give some special the special function. First is one-to-one function. What's the objective function? Here just the definition. So you will find this the special one-to-one function that is a special function. So how to describe this special function? We also using the prepositional logic expression to describe this. That means for all x, all y, if fx equal to fy, then x has to equal to y. Then you satisfy this condition, we can say the one-to-one function. So you will find many of things that describe the special function or function features we also use the logic expression.
Domain, range, codomain, all of those terms that we just learned. Let me go ahead and create a mapping of this. let's say my mapping looks like this, where A maps to 2, B maps to 1, and C maps to 3. Each value in the range, remember that the range is values over here that are mapped to. So 4 would not be included in the range. This is my range. 4 would be in the codomain, but not in the range. And we're saying each of those values corresponds to exactly one element in the domain. So 1 corresponds to only B, 2 corresponds to only A, 3 corresponds to only C. If, however, I were to add an element D in my domain, remember this is the domain, if I were to now add an extra element D, and that element mapped to 3, this is no longer a one-to-one function because this value in the range maps to 2 elements in the domain, and therefore it would not be one-to-one.
So just from this word meaning one-to-one, that means only one-to-one. So we have said many. For this map, we have the two ways, or sometimes we can say they have just maybe we have just the four ways. That means from the map, from the here is A, here is B, we can say it is the more one. More one means that we can say it is just the many. We can say the many just refer to one. Okay. And one refer to many. And many to refer to many. And one to one. So one to one just like this. And we know that here, one to many value, it is not function because it is didn't satisfy the function. We cannot permit only one input to output the many outputs, so it is not. And similarly, if just the many inputs refer to the many output, maybe it is sometimes boring. Maybe if the one to one, so we are just don't, maybe it is also boring, not exactly for the definition. So we only have the two ways in the just the definition of the function exactly one. Here is exactly one. So exactly one we have two ways. The first is only one, only one. But the second is maybe have the many. It is the many, many to refer to. So it also generate the function, but for one to one, we only map this, don't map this. So the one to one, just to refer to means that if you just give output input the one element n, we are just going to have one element for output. Similarly, if you just know one output, we also can influence that one input. So, yeah, one to one. So, how to describe this one to one? Also using logical expression that means for all A or B, if they are imaginary, then they are pre-imaginary to the B. So, if here, this percent, the other one means that if A not equal to B, then they are imaginary. So, if, so it becomes the counting. the second special function, the subject or onto function, because it is a special condition. Here also just using the logic. So from this describing our human segment and for every element in the something should be underneath the one element in the whole. For each the possible output should be have the input connected. Means here is the for each of the elements in the output should have some just the line control. It is clear. Means the each element should have one the next element or connect line. It is a four. You can say it is a four. Okay, the third is bijective. So you that can be seen they are both satisfied. So objective or just injective. It means one to one and just also have this on two. One to one and on two. One to one and the project. So this one-to-one exactly correspondence adjunctive. That means it is for each one house should be one-to-one and also four. Here is an example. So maybe from this word meaning one to one, we can say what means one to one, we have said only one, only one. So, but here I have the two, but onto, onto will find on. So for each element should be full. Beautiful. Each of the elements in the onto should have some onto, something onto. But here I have no onto. Neither one to one, no. Here I just give you example to show you about this concept. There's a special about three on one to one, on two, and just one to one. Here. And here, this example just from the picture may be easy to understand for a human. But from the first this way, this map or this machine, the A to B. And now we can say for each one we want to check whether or not we could choose to something on to. Yes, 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 on to, it is on to. And similarly for this, it's one to one, one to one. It is okay, no problem. So if they have every to the only one, whether or not it is on two, no, because for these elements they have no error on two, no error. Because it is one to one and that's very important. And this picture, and from this picture, whether to one to one, here is arrow one. It's on two. Yes, for each line we have something on two, arrow on two, on two, on two. So it is both one to one. So it is subject. Here is only subject. Subject is not subject. It is inject. Injecting that means one to one. So it also from the word means in one to one. Third, that means on two. And five, that means five. Five just to one, one both. Five both. So it is maybe and this. And here is the other way to use group. And this group you can just function the group. And also, what we know that functions can be seen as special relation, and relation can be described as map. So, function, function. And here just also to find the special the functions or functions of features. So this can be the increasing and decreasing. So increasing means that you will find right? The strict increasing just means if x smaller than y, that means x is increased. Then your the metric or your final absolute value is also increased. Then if x is smaller than y, then fx is also smaller than absolute. If not, that means x is smaller than y plus x is absolute value imagine fx larger than f1. This is a decrease. So decrease in just means when x is larger but y is smaller. This is it. When x increase, y is down. Here, when x increase and y also increase, increase, increase and decrease. And from this, okay. Now here just give you about the second book. Uh, so, so three, two, one, on to whether or not satisfy strict increasing or strict decreasing. And you can so no, you have to find one country example. So it is just from the definition. Okay, very well. For the two men, for the two. So sometimes you also can use the picture. For example, here as the last one is x plus sin x, and here is the picture. So on this picture, we can check, for example, 1 to 1. 1 to 1, that means for each value is only 1. So you can find, if you just using like this, so we are mapped. Here is the y, we are mapped here only 1. 1 x, here is x, here is y. That means we are from the same value, we are just only 1 x. So that means this is 1. For example, here, we know that we just the example from the video is fx equals to x squared. If it's just the x from this or this then you will find none. If it's just from this, you will find, for example, this 4. Here you find this, and so from this 9, we are just match. We are just match the two values from these two values. If two, so that is not 1 to 1. So 1 to 1, that means for each is the 9, you only keep 1. You only keep 1. You only keep the 30. But here you will find you only keep 2. Which means that for each is the 9 should match have something. Have 2. But here you will find some no 2. This all the picture is over 2. So you have no hit means that not 2. Not. And increase means just that when x is increased, whether or not y also. So it is just from this way, it is just from this group, then it is increased. For this is 1 to 1, here is 1 to 1, and on to, and here is the increase. Okay. And sometimes it can draw the picture, from the picture you can use it to sketch. Okay, now back to discussion time.
Bye, Loshi.
Any questions?
No, no, there is no question.
Okay, thank you. Thank you, Rosie. Bye. If you look at the today. Bye.
Thank you.
Thank you.